So next up will be Simon Glass, and he'll be talking about a hacking project that will bring U-Boot back to be working with Chrome OS, and he also will tell us about how to do firmware packaging properly. Please give it up for Simon Glass.
Hello everyone. So let me jump straight into it. This is what I'm going to talk about. First of all, U-Boot, verified boot implementations and how we might do it in Chrome OS. That's the most part of this talk. And then I'm going to do a little demo. And then I'm going to talk about firmware packaging depending on how the time goes. A thing called BinMan. So this is a bit about me. Everything you wanted to know about me. I've mostly been interested in ARM chips and electronics and Linux and that sort of thing. I got into U-Boot 7 years ago now when I was in Chrome OS the first time. And I ended up upstreaming things. And then after that, I dabbled in a fair different bits and pieces because basically my day job was kind of like a Java programmer, I suppose, except I didn't even do very much of that. So I used to go home in the evenings and fiddle with boards and that sort of thing. So I did quite a lot of stuff to keep my sanity while I was doing that. At the moment, I just maintain, I'm custodian of driver model and device tree in U-Boot. So I don't do anything like as much as I used to. And I'm particularly interested in runtime configuration and firmware, which is something that perhaps is traditionally not done in firmware, but I think it has a lot of benefits. So I guess if you've heard of U-Boot, you're here. It's a very hidden bootloader. Very seldom do you see a U-Boot logo on the outside of a device, but a large number of devices that we use in our day-to-day lives do use U-Boot under the hood. U-Boot is a very flexible bootloader, something which could almost be a fault. There's a large number of features that you can enable, most of the major file systems and networking and all this sort of thing. So it also has a test framework based around a thing called Sandbox, which is basically the ability to run U-Boot on Linux, just as a Linux program, which makes it much more convenient to develop your software, because developing it on a Raspberry Pi where you've got to swap the SD card back in and out is a serious pain. So at the moment, U-Boot supports 2 verified boot implementations. The first one uses FIT, the flat image tree, which is basically lets you select configurations like kernel, RAM disk, whatever, and sign them. And when you sign those, they cannot be mix and matched or anything like that. And the public key in a read-only memory or some protected memory is used to verify it. So U-Boot can boot through to the kernel and verify any images that you happen to load, FPGAs or whatever it might be. So that implementation is a few years old. It's used the talk last night about OpenBMC, which is a sort of data center system that uses that technology, and it's built into U-Boot as a core feature. More recently, U-Boot picked up Android Verified Boot, which is sort of like Chrome OS, actually. It's the way Chrome OS does things. It's got an A/B boot, and you can boot one and try the other if you fail, sort of thing. And that's used with Android things. But U-Boot doesn't actually support Chrome OS Verified Boot. It used to, but it doesn't, because basically the support is atrophied. So I thought, what would it take to get it running 2018, and what would it look like? It would be very different from the way it was those years ago. Why would I want to do this? I have a day job that does involve embedded now, so I'm not spending anything like as much time on this stuff in my spare time. But essentially, I think Chrome OS Verified Boot maps very well onto embedded devices. It's actually reasonably small. It's a fairly efficient implementation that actually runs on the device. It has some nice features like the firmware screens. Maybe you've never seen them, but if something goes horribly wrong with your Chromebook, it'll come up with a recovery screen and you can insert an SD card and recover the device and get it running again. It's got auto-update and rollback support, which is actually very robust, and it's got a good security record. I've mentioned U-boot already. And the other thing is that the Chrome OS build system is a pretty big commitment for someone to do. You know, if they're trying to build, I just want a bootloader and I just want to have verified boot. I don't want to bring in Chrome OS and, you know, all that sort of stuff just to get there. There is a bootloader, well, it's not really a bootloader, it's sort of a program, I suppose you'd say, that runs under core boot called Depth Charge, which you know, is what Chrome OS uses these days, but it's not really widely adopted. So my goal is just really to look at how it could be done, and can we have it so that we can just say, okay, enable Chrome OS boot on, let's say, a Raspberry Pi, and it will just do it. That's all you have to do, and everything will kind of work. That would be ideal for me. And I will say this is work in progress, so I haven't got there yet. This is just something that it's a starting point, I think. So here are some of the things that I think we want to use in a verified boot implementation in 2018 U-boot. So the first thing I mentioned is Sandbox. So actually the original verified boot, the implementation in U-boot, was written using Sandbox. It was entirely written on a laptop with no devices anywhere in sight. You can write your algorithms, you can run your debugger, you can do all of that sort of stuff without any embedded hardware and you know, develop everything. And then when you get it working, you can try it out on a device, but it should work. There's things like device drivers and so on, but anything to do with an algorithm, it's pretty much how I develop stuff. I can, in my little editor thing, I push F4, it builds it, takes a couple of seconds, and then it can run it, or I can manually run it on the command line. If I want to use the GDB, I can do that. So it's a nice environment. I don't really develop anything major on an actual device. The next thing is driver model. Driver model is something that's been in U-boot about 4 years. It's pretty much the means by which we get devices up in U-boot. So we say, essentially we have a device tree which describes all the devices and the drivers that are needed through the compatible strings, and then the U-boot at startup will go off and bind all those drivers, and then when they get used, they get probed. So obviously U-boot is a lazy probing. We don't probe anything unless we need it. So it's a little bit different from Linux, where you just have that probe step when it boots up. U-boot has this extra bind step because we really don't want to probe every USB and everything else you've got. Then we may as well run UEFI. So it's very much trying to just be a lazy init system. I mentioned device tree. I believe half of you hate it and half of you love it. Is that correct? This seems to be the story. For those of you who don't know what a device tree is, think of it like ACPI or something like that you may be more familiar with. It's a little bit simpler. The device tree implementation in U-boot is fairly efficient, uses roughly 3 kbytes of memory on Thumb 2 to get the basic library in place, so it doesn't have a huge overhead. And there are other features as well, and the final one is BinMan, which I'm going to talk about later on, assuming we get time, which is the firmware packaging. One of the things about verified boot is the packaging does become more complicated. No longer are you just getting a SPL in a U-boot or something like that in an image. Now you have to sign things. Particular areas are signed and the signatures have to go somewhere. And maybe you've got some images you want to display on the screen as well. They have to go in the firmware image. And so the firmware packer becomes a little less trivial than perhaps just, using DD or catting two images together. At the moment, U-boot uses binman for, I think, Tegra and x86, maybe SunXI as well. Okay, so let's talk a little bit about Sandbox. I just want to, I'll show you it later actually, but essentially it allows U-boot to run on Linux. It supports most subsystems, so you can, for example, type USB start, the command line, and it will go and scan and find a fake flash stick with, I think, 1K of space on it, and it will go and you can read it and that sort of thing. So there's quite a lot of functionality in there, and all of the testing in U-boot relies on Sandbox. It actually does run on any other board as well, but the one that runs on Travis, CI, and so on is basically using Sandbox and a bit of QEMU. Most of the core features, at least in driver model, have a good set of tests. It also supports TPL and SPL. Have any of you heard of those things? Yeah, one of you, okay. So briefly, we use TPL to load SPL. TPL is often very small, a few K. And then we use SPL to load U-boot because SPL sets up our memory. Until we have memory, we can't load U-boot in because it's too big. And so some systems you don't have them, some systems you only have SPL, and a few systems you also have TPL. But Sandbox supports those and lets you run those things. It also lets you save state over runs. So let's say you have a TPM driver which has some rollback information. You can run Sandbox. You can then run it again later, or run a separate test later on, and it will read in that state and carry on where it left off. It even lets you persist the DRAM across runs, which is actually useful for testing because you want to set up a case and then run it multiple times perhaps. So my obvious plan was to use Sandbox to bring up verified boot, Chrome OS verified boot, and that's what I've done. So driver model is pretty much based around the concept of a U class, which is like a real-time clock or a USB controller or SCSI or whatever. Each of those things has its own API, and each of these things have device tree bindings taken from Linux, essentially, to provide properties to those devices. I mentioned it supports lazy init. It also supports the command line. You can see the devices at the command line and so on. There's a talk down there that you might want to look at, or just search for U-boot driver model if you want to know more about that. Device tree. Actually, this is cool. You won't be able to hear it, I'm told. But device tree, so there's no point in doing this. I'm going to do it anyway. Device tree has a song. Did anyone know that? Oh my God. It says it's the only configuration language with its own song. It's sort of like to the tune of the Flintstones, so you need to look that up later on. It's basically just about runtime configuration. You put all your configuration in one file in one place, and then everything goes from there, rather than having to put all the different configuration in all different files and write it in C code and that kind of thing. The idea is that maybe you can run exactly the same U-boot on 10 different types of hardware and just put the device tree in for each one. And then there's some various other random things. It seems a long time ago, but U-boot didn't used to have kconfig. So I think, define Chrome OS, actually should spell it correctly when I do that, to enable the features automatically. There's a logging system now which would be useful to use, just so that you can log against different U classes and that kind of thing. It just lets you say, okay, I'm debugging the TPM now, show me all the TPM logging, that kind of thing. I'll mention the phases of U-boot in a minute. And in terms of being able to boot other stuff, U-boot sort of already does that. So it can run a lot of stuff. In fact, to talk after this, I think it might be in the other room, is U-boot's EFI features. So the ability to run EFI apps and boot grub and things like that, which is something that U-boot does. So it does the other stuff, if you like, very well. There's also boot stage, which is a timestamp duration system. Okay, so let's just talk about the boot stages. This is specific to Chrome OS. So this probably looks a little confusing, but let's just look at this bit over here. This is the TPL, the tertiary program loader. This is what we first execute when the machine starts up. Now, what we want to figure out here is, do we want to do A or do we want to do B? One of them is going to work, one of them may be broken. One of them might be the new version, one of them might be the old version. This is how we do upgrades. We upgrade one and then boot into it. So the firmware selection happens here. That's actually where a large chunk of verified boot's going on. Once you've done that, you go into SPL, you set up your SDRAM, because remember, it's not ready on startup. Why do we do the SDRAM after we do the firmware selection? Anyone know? I'm going to tell you anyway. Well, the problem is the DRAM setup code might be buggy. We might have to upgrade it down the track, which I could tell you a horrible story about that because it actually happened. And we ended up writing code to checksum and correct the memory after resume because of that. So it's a lesson that we learned. Once you've set up the SDRAM, you then go to U-boot itself, U-boot proper. Again, you have two of them, an A and a B. This is where the real code is. There's loads of code here. We've got full UI, and maybe we've got, anti-aliased outlined fonts and images and all sorts of stuff. We can go to town here. And then finally, we boot into Linux, A or B again. If things go horribly wrong in neither of these systems, neither of these things will verify and work, or we die or crash along the way, we end up in recovery. And that's where we have a recovery screen, and we try and show people what's wrong and let them put a USB stick in or an SD card and recover the system. So we have to have that as well. We have to have that in effectively read-only memory so that we can never brick the device. These are some of the things that I wouldn't bother implementing, and I don't intend to with this Chrome OS thing. U-boot has a lot of other things that can be handy, scripting and file systems, network booting for factory and that sort of thing. But that's already there, so I'll just leave it alone. So this bit of the talk is just going through driver model and how it's used. It just shows you what I think is a fairly elegant way to put the system together with the device tree, configuring it, the code, selecting what's done, and so on. So these are just fragments. Don't try and type this code in; it's not going to work. Just fragments to show you how things work. So the first thing is there's a U class in U-boot called block, the block device. And lots of things have a block device. So if you've got an MMC controller, it's got a block device. Same with USB and SATA and so on. So this is effectively the driver model tree. It's a tree of devices. And you can see at the bottom we've got every one of these things has a block device. The one that's out on its own over there is actually the Sandbox one. Sandbox has a block device, but it doesn't have a parent. Now we can iterate through those block devices. We can just say, give me all my block devices, probe each one, and is there a file system available that I could recover from? So for recovery, we just simply go through and iterate those block devices and find anything that's plugged in, whether it's USB stick or SD or whatever else. There's also a sysreset U class, and this one just lets you reset the system or find out why it reset last time. This is the driver. It's pretty much the entire driver for x86 sysreset. You can see down here the driver. You can see the compatible string, which matches the compatible string in the device tree over here. And you can see some methods, including this one, which is request a reset. Depending on the reset type, you send out a value out some special x86 port to make the thing reset. So that's a reset driver. Chrome OS needs to reset, so we'll just have it define that driver, and pretty much any platform should be able to define a driver like that. And then it's sort of separated out from the core code. The next one's a little bit strange, but essentially we want to be able to read from the firmware, and I mentioned that the firmware is complicated. The firmware image is very complicated actually. I'm not going to bore you with the details. But here we have, we've actually invented our own new class, and this new class is called a firmware store. All it supports is read-write and checking whether whether write protect is enabled. Those are the three operations it supports. So you could imagine implementing those operations very easily with a SPI flash device, or maybe with an MMC device or something like that. So there's a level of abstraction, between that and how you actually implement it. Here we've got, we can show that it's implemented by SPI. There's a configuration node up here that's saying, okay, my firmware storage is this thing, and you follow that link to here, it's a SPI flash. And so we're going to have a driver which knows, basically is a firmware store driver that knows how to talk to SPI flash. I haven't shown you any of the other code that implements this, but essentially it means that when you start up, all you do is you say, give me my firmware store, and you can start reading from it. You don't have to worry how that's provided, or how that comes about. The driver model takes care of that for you. Similar to that is non-volatile data. So one thing you have to do with Chrome OS is you have to have rollback information, but you also have things like, do I want to go into recovery this time? Did something happen did I crash last time? That kind of thing. So we have a couple of different things. We actually use the EC. There's an embedded controller, a little Cortex M3 Micro on Chromebooks. And we can send that a message and say, please go and write some data for us, 16 bytes of data, or please bring it back, that kind of thing. And it stays around over the reset of the AP, the main CPU. It stays around because the EC doesn't get reset in that case. So we have a driver here which basically implements, this is a function within the driver. It says, read this data in this size. And we just go off and find our parent device, which is where this thing here, so our parent is up there. It could be a real-time clock, or it could be a Chrome OS CC. If it's a Chrome OS CC, we just go off and make that call. So we can implement, the way I've done this is implemented 3 different NV datas. One is using the real-time clock, because some devices just use the CMOS RAM for that. Using the TPM, because some of the data is what's called secure data. We need it to be protected. We can't have it disappear, and we have to know that it's valid. So we put that in the TPM. And the third thing is with the EC. So we can say, okay, please give me the data, and I haven't shown you exactly how it works, but give me the secure data, please. And one of the drivers will put its hand up and say, I've got secure data, here it is. The other 2 will say, no, I don't know how to do that. So we walk through the available drivers until we find one that puts its hand up and says, yeah, I've got that data for you. So again, it's a fairly elegant way to do it. It's entirely configured in the device tree. So we simply put, in our RTC node, we put an NV data. Now here we can put an NV data. Wherever we put the NV data, its parent is the thing that it talks to get it. So it's configured through the device tree at runtime and in a single place. vboot flag is a little bit similar. We can, we can go into recovery mode. We have different, whether the lid is open or not, whether the power is, the power button is pressed, and so on. So these are all just configured in different ways. So this is a GPIO. The lid open is a GPIO, so we specify which GPIO it is. The power off button on Sandbox is just a key that you hold down when you want to power off. So that's just the key number. I mean, it's a bit random, but the developer flag is just always on. It's constant 1. So you can hack around with this configuration and change the way the system works. And that information effectively gets down into all these different drivers. that you have here. This one here is basically walking through all the vboot flag drivers that it can find, and it's trying to find the flag that you've asked for. If that driver supports it, it will call that driver to get the value. Global configuration is pretty simple. We have just basically two ways. One is using kconfig, which you're probably familiar with, just define a kconfig and then check if it's enabled and do something. And the other is to actually put properties in the device tree, so you can say, okay, the EC takes a long time to update, and then at runtime you say, if it's a slow update, set a flag to put up a big scary update screen telling the user to wait. So that's a way to make configuration work. Notice that neither of these is changing the build. I can use exactly the same U-boot image here, just put in a different device tree to make it behave differently. I won't go into why it's useful to have a smaller number of builds. You'll probably figure it out for yourself, and probably many of you have hit this problem. Is every time you have something new, you have to test it. So what's the current status with all this messing about? Well, Sandbox boots to the kernel and kind of everything works reasonably well, which you might expect because that's what I use to do it. For bare metal, I've been fiddling with this laptop here, which sort of works, and I'll show you in a minute. It's basically x86. It's the Chromebook Pixel 2. And then with Core Boot, there is actually a U-boot target that is designed to run on top of Core Boot for x86 platforms. But I haven't, and that's actually what the support used to use, but I haven't actually resurrected it. It's pretty straightforward I think, to be able to do that. And then I've got a video game console at home that runs a Raspberry Pi 3, so I'd like that to run Chrome OS Verified Boot. I think that would be cool. So I don't know when I'll get to that, but we'll see. Current status is, this is kind of working, this is, well, it's demoable, and then these two not so much. Speaking of which, now I'm going to try and do a demo. Please hold your laughter to the end and see if I can do this. So here I am at a prompt, which I hope you can see. And I can run U-boot basically. So that's running U-boot obviously under Linux, but it looks the same as it would on a board. If you actually used it on a board, that's pretty much what it would say. And you've got your commands, and you can do various things like reset to quit and so on. But it is basically U-boot. If I type dm tree, you can see all the devices that are in the system using the driver model to have a look at what's available. So that's Sandbox. So let's just run the U-boot, this thing. So this is basically the command line I'm going to run, which I'm going to explain briefly. So I'm running U-boot's TPL, which is, if you remember, the very first stage before SPL and before U-boot proper. Okay, so that's just a program that you run. That will in turn run SPL, which will in turn run U-boot proper, right? I'm telling it, please use this device tree. This is something that Binman has produced. This is just a logging level. This is the command that I want to run. I want to bind this big path, which is a Chrome OS image, essentially, that I built. And then I want to say vboot go auto, which just means vboot. However you want to boot, verified boot, just do it. Do the correct thing for whatever stage we're at. So that's basically what I'm going to run, so let's do that. And we get a whole lot of stuff. So let me just take you up a little bit so you can see this. So the first thing is that we're starting up here. Where are we? There's quite a lot of stuff, unfortunately. We're starting up in TPL, U-boot TPL here, and we first of all run this version, this init stage, which we're trying to verify that everything is okay. We read the flash to figure out what's in the flash. We found these things in the flash. And now we're going to go and do all the initial verification. And this basically ends up with us saying, okay, we're going to boot from slot A. We've decided that's what we want to boot from. And once we do that, we figure out where it is. We hash the firmware and check that the hash verifies as it should. We have some unimplemented EC commands. There's an emulation of a Chrome OS EC in U-boot. It doesn't do everything, but it probably should. I don't know what those commands do. Hopefully they're not important. And then we have a thing called a blob list, which is relatively new. It's not really in mainline yet. And that essentially lets you pass information between the stages, TPL, SPL, and so on. We then go into SPL. All that really does is set up SDRAM, which doesn't happen in Sandbox, and then jumps into U-boot. And then we do a similar sort of stuff again, and then we end up in this loop where we're pretty much going to try and boot the kernel. And in fact, it does, as you can see, boot the kernel. On Sandbox, all it does is find the kernel and exit. But in a real system, it would actually boot it. If we run it with the LCD on, you can actually see what's going on. This is obviously the recovery. Well, sorry, it's the developer mode screen. You can change your language, and you can go out of. You can decide that you want to turn verification on and that sort of thing. So all the screens work. Sandbox has a pretty good system for displaying this stuff. So that's basically a demo of it running. And I'll just show you a demo on this device, which is going to be interesting to see how I can do this, but let's just try it. So this is again it running. And I just wanted to show you the lazy init thing that I was talking about. One of the problems in Chrome OS has is that when you start up, you don't normally want the display on in firmware. It takes about a second to turn the display on, run the boot ROM and everything else on this device. So we don't want to do it most of the time. So the way U-boot works is that if you don't need it, then it doesn't get inited. But if I type a command, then it will actually, you can't really see it, but there's a little cursor now, it's inited the display. All they did was tell it, please set your standard out to the vid console. And that caused it to probe, oh yeah, I need the video console. Okay, no problem. Now I need to run the PCI boot ROM, option ROM, and all that sort of stuff happens lazily. So the end result is that when I boot the machine, it normally wouldn't do it, but if it sees that it has to, it will go off and init the display automatically. So that's a nice thing about driver model. If you want to see that better, you're welcome to come up at the end. So that's my demo. And then I just want to talk a little bit about what the plan is. A lot of the stuff will land in the next 2 releases. And when I say stuff, I mean the non-Chrome OS stuff. Actually, as to the Chrome OS stuff itself, I'm not sure there's this much code. I'm not too sure what the best thing to do is. We'll just have to see and how much interest there is in that sort of thing. But I'll take it that far. Okay, so by my count, I've got 2 minutes left, and so I'm not going to go into this in any great detail. But let me just go through this quickly and talk a little bit about BinMan. I don't mind if we don't talk about it at all, but I'll just mention it at least. So this is my motivation. Obviously, firmware packaging is becoming more and more complicated. BinMan does all of these things. Essentially, you create an image with a list of entries. It packs them together. It does whatever needs to be done to them, and then you end up with a final image. And the image that I was running in Sandbox before and on this device, they were produced by BinMan. Here's an example of an image. We have SPL here. We have some padding to 32K, and then we have U-boot. Very, very simple image. Here's how you describe that in BinMan. You say, okay, here's my image size. Here's my pad byte. I want SPL, then I want, U-boot at this offset, and it will automatically put padding and that kind of thing. So it's very simple to put things together, unless you're on x86, where it's a total disaster because there are so many binary blobs and so many bits and pieces that have to go in there. In fact, the way it works is there's only a single x86 file which does everything, and you can see that's why it's got these if-defs. If we've got an Intel FSP, then we shove it in here. If we don't, then we don't. I'm being told to go to the end here. So basically, my intention with BinMan is to make it be able to build a Chrome OS image, which it can, but I think it needs a little more work. And there's a few links there to BinMan if you want to read the documentation and the entry types. It's pretty easy to extend and hack if you want to try it out. And I won't play this video. Unfortunately, I'm very sad. I wanted to play the video, but there's no sound, so there's no point. Please buy your family Chromebooks. It helps keep me employed. Thank you. Any questions?
Thanks. Give a round of applause. Whew, I'm so glad I don't have to tackle you.
Tackle me?
I promise to tackle anyone who maxes out the time. So
you're just happy I didn't take 10 minutes.
No, it's fine. So yeah, any questions? Oh, over there. Okay.
So during your sandbox demo, I saw some lines scrolling by that said something about CBGFX. Did you hoist any code from libpayload into Ubu to support the graphics, or where did that come from?
Oh, yes. That should be on the to-do list. The graphics, so all U-Boot provides is a frame buffer and a video and what's called a text console, which has, nice fonts and things, but no actual graphics. So yes, that code is simply brought in and needs to be removed or something because it's, but there is no U-Boot equivalent, I don't think, at the moment. You can draw bitmaps in U-Boot, but I think it does scaling of bitmaps as well, which I don't think U-Boot does at the moment. So yes, good. Well spotted.
So you're not considering porting that over? Or?
Sorry?
Are you considering actually porting that over to U-Boot or just replacing it with something else or something?
I don't know. It's hard to say. This is one of the weird things about Chrome OS. It has all these features. And sometimes, U-Boot is a bootloader, right? I suspect there's value in it, actually, because anything that has a display, you probably want to be able to show something on the display and say, I can't boot or whatever.
Okay, cool.
We'll see.
Any more questions?
To quickly piggyback on the graphic stuff, we were sort of having the same question about Petit Boot earlier, and Alex Graf, who may not be here because he's presenting downstairs in 5 minutes, mentioned there is a library here you might want to look at, so talk to Alex maybe. There's something out there that he says is interesting. Regarding your talk, well, thank you first, and I noticed you took some liberties with the device tree.
I took some what, sorry?
Liberties with how you put things in device tray.
Absolutely.
And
I'm religious on the matter.
I assume you have no intent to get that through any binding document.
To what?
Through any of the binding definition process. There is an open question, and it's something I think is worth some of us thinking about, is this whole concept of having those pseudo devices in there that are effectively used as a way to group various low-level functionalities into a virtual pseudo device. And in some cases, you've been sticking things in your /Chrome OS. In some cases, you have been putting things as children of the device providing the parent functionality. Yes. Go big back and forth. Do you have any particular reason why you prefer one way or another?
So there is a way to say, here's a device tree that I want you to merge with my normal one. The x86 tree has a uboot.dtsi, and that just gets attached to any x86 thing. So you can put overrides and things like that in a separate place. So it's not like we have to pollute the pristine Linux kernel device tree or anything like that necessarily. So I don't have a particularly strong point of view. The advantage of having it in a config block, as you saw with my example, it's all in one place and you can go, oh, here's my p handle to this, But when you're writing a driver, it's a pain to go and find all that stuff. The driver just it's easier for the driver to just say, where's my parent? My parent is my parent. If my parent is Spy, then I know it's Spy, I can talk to it. So I think I probably prefer the latter, but I don't know. I will point out on the device tree side, uboot doesn't have a user space. Linux's attitude is, well, you put all your information in, all your decisions and so on go in user space. Uboot doesn't actually have a user space. So that's one justification for putting config in device tree.
Unfortunately, that's all for questions now. So thank you very much. Give a round of applause.
Thank you.